All right, everyone, welcome. Today, we are jumping into one of the biggest battles in organic chemistry, a real rank decider for your CUET exam, SN1 versus SN2. Trust me, this is where the top ranks are won or lost. So let's get right into it.
So let me ask you, is that constant confusion between SN1 and SN2 costing you precious marks? Well, we're going to end that confusion right here, right now. In the next few minutes, we're going to master this whole topic and lock in those marks for a killer rank. You have to stay with me till the end, though, because we've got practice questions and memory tricks that you absolutely cannot afford to miss.
So you might be thinking, why all the hype? Let's get straight to it. This isn't just some random chapter. It's a super high-yield topic. It's basically a gold mine for your CUET score.
And here's the exam blueprint to prove it. You're not just going to get simple questions. We're talking conceptual deep dives, tricky assertion-reason formats, and questions that test your grasp of stereochemistry and the actual mechanism steps. And here's the best part. There are guaranteed questions on this every single year. Plus, it links directly into haloalkanes, alcohols, and stereochemistry. So the bottom line is, if you master this, you're not just scoring here. You're boosting your score across multiple chapters. It's a huge win.
Okay, let's set the stage. We're diving into the two main reaction pathways. The whole game revolves around one core idea: nucleophilic substitution in haloalkanes. If you get this, you're halfway to mastering both SN1 and SN2.
So what even is nucleophilic substitution? It actually sounds more complicated than it is. Imagine you have a haloalkane, Rx. The carbon atom is a little bit positive, and the halogen, X, is a little bit negative. Now along comes a nucleophile, a species that's rich in electrons and looking for a positive charge. It attacks that positive carbon and, boom, kicks out the halogen, which we call the leaving group. The nucleophile takes its place. That's it. That's the entire reaction in a nutshell. First up, let's talk about the SN2 pathway. I want you to think of this as a quick, perfectly timed surprise attack. The nucleophile sneaks in and attacks the carbon from the back at the exact same time that the leaving group is leaving from the front. It's a single coordinated move. We call it a concerted step. There's this brief, unstable moment called a transition state, but there's absolutely no intermediate formed. It's all over in one swift action.
So let's break down the must-know facts for SN2. It's a one-step mechanism, no intermediate. The stereochemistry is super important. You get an inversion of configuration. The best analogy is an umbrella flipping inside out in a strong gust of wind. The rate of the reaction depends on both the haloalkane and the nucleophile. That's why we call it biomolecular. It absolutely loves strong nucleophiles and polar A product solvents like acetone or DMSO. And here's the golden rule. It works best on substrates that are the least crowded. So primary is fantastic, tertiary is a no-go.
Now let's meet the rival, the SN1 pathway. This one is completely different. It's more patient, a two-step process. In the first step, the leaving group just leaves, all on its own. This creates a carbocation intermediate. Now this first step is slow. It's the bottleneck, so it determines the whole reaction's speed. Then, in the second step, which is super fast, the nucleophile comes in and attacks that carbocation that was just formed.
So the key features for SN1. It's a two-step mechanism, and the star of the show is that carbocation intermediate. And because you have a carbocation, you've got to watch out for rearrangements. We'll talk more about that. The stereochemistry is called racemization, meaning you get a mixture of products. The rate? It only depends on the haloalkane, so it's unimolecular. SN1 isn't picky, it's fine with weak nucleophiles, and it loves polar product solvents like water or alcohol. And crucially, its substrate preference is the exact opposite of SN2. It wants the most stable carbocation, so tertiary is king.
Okay, it's time for the main event. Let's put SN1 and SN2 head-to-head in a strategic showdown. This next slide, this is your ultimate cheat sheet. This is how you'll decide which mechanism is happening in almost any question they throw at you. Look at this table. It's pure gold. Let's run through it. Steps: 2 for SN1, 1 for SN2. Intermediates: carbocation for SN1, none for SN2. The rate law depends on 1 thing for SN1, 2 things for SN2. Substrate preference: totally opposite. Nucleophile strength: SN1 is okay with weak ones, SN2 demands a strong one. Solvent: polar product for SN1, polar A product for SN2, stereochemistry, racemization for SN1, inversion for SN2, and the big one, rearrangement is only possible in SN1. Screenshot this, write it down, commit it to memory. This is everything. I really have to stop and emphasize this point because, mark my words, this is a classic CUET trap. In an SN1 reaction, if that carbocation that forms can become more stable by shifting something around,
like a hydrogen or a methyl group, it absolutely will. It'll go from, say, a secondary to a tertiary carbocation in a heartbeat. You have to be on the lookout for this. It's one of the favorite tricks that question setters use to catch students off guard.
All right, now for my favorite part, the secret weapons. I'm going to give you a few memory tricks that will make all this information stick in your brain, so you can recall it instantly when the clock is ticking during your exam.
Let's lock this in right now. For SN1, the 1 reminds you that one molecule is in the slow step, and it forms one type of intermediate, the carbocation. Easy, right? For SN2, the 2 tells you there are 2 molecules in the rate step. And here's a little visual cue. The letter B in backside attack has 2 loops. For the solvents, just remember this. Polar protic solvents are perfect for stabilizing the positive charge of the carbocation in SN1. See? Simple. Okay, enough theory. It's time to step into the ring. Let's enter the live exam practice zone and apply what you've just learned. I'm going to throw a couple of CUET-style questions at you. Get ready to test yourself.
Here we go. First question, a straightforward MCQ. Which of these substrates is the most reactive towards an SN2 reaction? Look at your options carefully. Think about the #1 rule for SN2 reactivity. Go ahead, pause the explainer right now and solve it.
Did you get it? The answer is C. And why? Because SN2 is all about avoiding crowds, what we call steric hindrance. It needs a clear runway for that backside attack. Option A is a bulky tertiary halide, B is secondary, but C is a lean primary halide. It's the least crowded, so it's the fastest and most reactive for SN2.
Okay, let's ramp up the difficulty. An assertion reason question. The assertion is, SN1 reaction is accompanied by racemization. The reason is, the intermediate carbocation is planar. Now think about the relationship here. Are they both true? And does the reason correctly explain the assertion? Choose your option.
And the correct answer is A. This is a perfect example of how these concepts connect. Both statements are absolutely true, and the reason is the perfect explanation for the assertion. Because that carbocation is flat, it's planar, the incoming nucleophile can attack from the top face or the bottom face with an equal 50-50 chance, and that is exactly what leads to the racemic mixture.
Okay, I need everyone to listen up for a second. Let's get serious and talk about the high alert zone. These are the common traps, the easy mistakes that students make year after year. Knowing these will save you from throwing away marks you deserve, so pay very close attention.
Here are the top 5 traps. Number 1, forgetting about rearrangement in SN1. I've said it before, I'll say it again, always, always check. Number 2, ignoring the solvent. The solvent is a massive clue the question is giving you. Number 3, mixing up the stereochemistry. Say it out loud. SN1 is racemization, SN2 is inversion. Drill that in. Number 4, misjudging the nucleophile. A strong one like hydroxide screams SN2. A weak one like water whispers SN1. And finally, number 5, confusing the rate laws. Don't get unimolecular and bimolecular mixed up in the heat of the exam.
All right, we are in the final lap now. Let's do a lightning-fast recap of everything you need to know. This is your high-yield summary for that last-minute revision right before you walk into the exam hall.
Let's go. SN2, 1 step, backside attack, inversion, primary is fastest, strong nucleophile, polar aprotic solvent. SN1, 2 steps, carbocation, racemization, tertiary is fastest, weak nucleophile is fine, polar protic solvent. Key takeaway, stereochemistry is different for both. Remember, rearrangement is an SN1 only game, and it's a huge source of tricky questions. And the rate determining step is simply the slowest step in each path. Got it? Good.
So, how'd you do on those practice questions? Be honest. Drop your score in the comments below. I genuinely love to see how you did. And hey, what other topic is giving you a hard time for your CUET prep? Let me know, and it might be the star of our next explainer. If you're serious about crushing this exam, make sure you're subscribed so you don't miss a thing. We'll see you in the next one. Keep up the amazing work.